Friday's lecture or for the hands-on session, I think it's very useful to look around and make yourself familiar with, okay, where can we find optics? And I think that's also maybe the first question before I give some examples.
And then just before Bene starts on the content, I forgot to mention, I think one aspect of diversity of approaches and thinking, Bene didn't take the traditional route of what you think about starting as an undergraduate and then going into, he took a very different, you want to say a word about your personal journey to science?
Yeah.
So that is also very inspiring and reminds us that you can learn and pick up whatever you want independent of which backgrounds you come from.
Yeah, so I think the system in Germany is generally a bit different. So there's not undergraduate credit. You always have to do a master in order to do a PhD. But so I did an apprenticeship. So that's something where you learn something. Well, usually together with the company. So you get a salary and you do that for 3 years. And I did. I became an electrician more than 10 years ago, and then I started studying after doing my civilian service in Canada for some funny reason, and then. I was lucky to finish my master with Zeiss actually, because Nikon refused to let German people do their master there. And then I started my PhD in Vienna for microscopy. So I don't have a high school degree, and I also did not really go to university. So it's, and now I think I never would have guessed that I may end up in Stanford. So here I am. So and the talk I give for the introduction about optics is similar to what I did last year, but of course today it's a bit more hands-on. And I'm excited to hopefully raise curiosity a bit. And also maybe before I start, that's what was talked about. Maybe everybody thinks about something where life without optics for everybody individually doesn't work. So you get up in the morning, so what is the first instrument you have in your hand which could not work with the optics? Anybody? Yeah? Oh, that was handshake?
Well, I'll say my phone.
Your phone, yeah, that's very good. So the first motion in the morning is like getting up and then, hello everybody. Yeah. I think the phone is like the best example for optics, because in order to actually fabricate the electronics, you need a hell lot of optics, like the lithography, the lenses. There is a whole bunch of different sensors in there, like distance, time of light, and 3D sensors, and all kinds of stuff. And so I think this is really the best example for optics. And during this lecture, and maybe also on Friday, I would like to show you how you can rip it apart and take all the cool stuff and make a fancy instrument for science out of it. So but let's start with the very beginning. Yeah. So what means light? So photonics is basically the technology between light and optics and electronics and technology. And it all started with, of course, fire and what's light and incandescent light bulb. But there are also very funny effects in nature. For example, these butterflies, they have a nano structure on their wings that causes, let's say, the light to behave in a very funny way. So it's a little bit like, what's it called, the near-field optics effect, plasmonics, etc. So it's like a little bit quantum effect, and this is already there for like ages. So definitely we did not invent the quantum effects.
Just as a personal experience, for the first time in my life today driving, I saw a car that I think had structural color paint. Has anybody seen that? I was shocked. So when the car passes by, it was golden, and then when it was a little bit far, it was purple, which is exactly what happens, that with the structural colors, the angle that you look at it, but the fact that they've figured out a robust paint is super exciting, because think about, if it's a paint, it must be cheap. And this is how you should always be thinking about that. That implies that there is a capability that you can utilize in building the instrument. I was just so excited when I saw the butterfly.
Could also be that this is a dichroic effect.
It could be a dichroic effect. I was thinking about that it might not be structural color. But I would doubt to do dichroic is super hard.
It's kind of difficult on the large scale.
Yeah. Anyway, let's figure it out. I think it would be fun to know which paint that is, and bringing some of that paint might be fun.
Sure.
You can think about making all kinds of things at massive scale because it's paint.
Yeah, that's true. Yeah, and some other aspects where you, of course, maybe wouldn't have expected optics where it's important is glasses. So I see some people wearing glasses. I think what I put up here is like the first painting, somebody wearing glasses. So it's actually not so easy to manufacture a piece of glass that is well corrected in order to improve your eyesight, because the eye, even though it's very bad, I should maybe have put up the point spread function of your eye, which is surprisingly bad. Your brain is basically able to compensate most of the effects that are coming from degradation of the lens, because the lens itself is also not ideally shaped, let's say, in order to form a good image. But the brain is doing lots of processing. I think that's also something I'm coming to later. And of course, optical mouse and everything that produces light. You can see that even from the space station, for example. Photonics in general, there's a huge market. As I said, these machines that produce electronics, these lithography machines, they are mostly coming from the Netherlands. ASML is one of the big players. And one of the machines is roughly in the range, I think, of 1 billion euro. They last for like forever, and they produce tons of things. And the next generation is also more towards optics, so that you go away from electron-based chips, let's say, but you, for example, do the bonding intra-chip using fibers. They are just much faster. They don't have these impedances and stuff like that. So there's a whole new chapter opening. How do you connect different circuits optically, and how do you test them? And it's super exciting. And also, the world is connected through optics. So the fibers that go from one continent to the other. It's just insane what's the data bandwidth. Imagine talking to my family every day, and the lag is in the range of some milliseconds, and this would not be possible without optics, of course. And so this is all very exciting. As I said, the phone itself has a bunch of very fancy sensors. I think what's the most exciting to me is the 3D scanner, which is in the newest iPhones, where it projects a point cloud on your face, and from the correlation of the different points, it can reconstruct your three-dimensional shape. So, and it's not only fancy that it's working, but it's also insanely cheap. So imagine these sensors, they cost something like $5 when they are getting produced. Same with the camera. So I brought some from the lab. It's insanely well corrected optics. What you see here on the left hand side, that's a patent. I think it has not been produced by Apple, but it's from Apple, where you fold the optical train in order to have a zoom lens. So you have a periscope like in a submarine, and the different lenses, they move with respect to each other. So you have to have optics that are well characterized. So they have this funny shape. It's called a sphere. So it's not just a sphere, but it's mathematically well defined. And these lenses move relative to each other, so you need a little motor. I brought two of those. The first one is a voice coil motor, so it's something like your speaker. It can move back and forth in nanometer precision. And the other one is a motor, like from a CCD lens here. And so these modules, if you produce them, they cost a fraction of $10. So you can imagine what's the scale for the manufacturing there in order to make it cheap. So I mean, a whole phone costs something in the range of €500, and so every component has to be very cheap, and hence very well.
Do you want to pass those?
Sure.
People want to hold.
So what I'm passing are actually multiple different things. So this is from the optical pickup device from your DVD Blu-ray player. I'm coming to that later. Just very interesting to see. This is a focusing lens from a CCTV lens. It's motorized, and this is a lens from I think a Huawei camera, and this is just the voice coil motor for a larger one. I can just give it around to see. I think there's not. Yeah, you can find that in many different.
Yeah, and I think one thing about Friday would be is you should look for parts like these in used electronics or anything that you find and scavenge it yourself as well. Yeah. Because it'll give you a better intuition of how they are used. So we can pass these along that way and then swap.
And maybe also one aspect which I almost forgot to tell you, the backlight illumination of your phone. So this here is an OLED, which itself is already super exciting. But if you have like the old style LCD type cell phones, and imagine you have a perfect uniform illumination of a screen that is roughly 9 or 7 inch large. I don't know, not 7 inch, some centimeters at least. And the way it works, you would expect maybe that behind the screen there's a whole bunch of different LEDs. That's not the case. So there's only, say, 3 LEDs in the lower end, and then there's a very interesting mechanism. It's called BEF, brightness enhancement film. It's on the right hand side here visible, where you have a light guide where the LED is guided through a piece of plastic, and then this sheet which is sitting on top, it's a small grating formed by prisms. It's coupling the light out in the way that it's completely uniform across the whole field of view. Yeah, also manufacturing wise, this is super exciting because it's super thin.
Yeah, I think one way of thinking about this is because it's done in plastic, this can be embossed. So you can really print it technically.
Yeah.
And then of course the scenario for if you were to think about designing, and even in terms of how some of these TVs work, is the fact that you can get these larger and larger and larger displays is not the same. The cost doesn't scale linearly with the size of these displays.
Yeah.
Because the pixels cannot generate that much amount of light. You really do need backlit.
Yeah, that's a different story. I mean, so these displays, if you have like a 50-inch large screen, they are produced in one piece with one photography machine, which is listed, which lies on the left hand side actually. That's, I don't know how they do that, but it's really interesting. Another aspect where photonics is very important is industry. So nowadays, so that's something I've seen recently. Sometimes you have the problem that when a turbine is hit by something in the air, let's say a bird, you eventually need to replace all of the blades because it's broken. And so what they came up with is you just mold just a single blade on top of this whole thing so that you can reuse it. And the way it's done is that you have a laser with a very high intensity laser power, which is like in the range of 10 kilowatts, and then you just have a stream of particles made out of some special iron, and then you basically weld in 3D, so it's a 3D printer, but with metal. And so this way you can update your parts without actually throwing them away. Pretty cool. Some other aspects, the LIGO for detecting gravitational waves, it's basically just an interferometer, going to a bit more detail later. And yeah, so but as I said, what's exciting for me the most right now is microscopy. And so just for you to get to know where I am situated. So Jena is the place for microscopy because Carl Zeiss, I know who may know him, and Ernst Abbe, they both lived there and also founded the company Carl Zeiss. And it's in the center of Germany, and there's this monument with this formula, and the formula basically dictates certain properties for optical resolution, and I will come back to that also later. So, microscopes.
Did Zeiss and how did they meet? Do you know the backstory of?
Yeah, so
because one was more mathematical, one was more entrepreneurial.
Yeah, so I think I'm not quite sure there were more people involved. Like,
I see.
So, but one produced the.
Well, what I was surprised was I didn't know that Ernst Abbe was part of founding of Zeiss. Okay.
Yeah, but there were more people involved. So one was able to build the tripod, and the other one did the math, and then they came together to build the instrument. Yeah. That's the rough story. Yeah. Right. So I think most of you may know these pictures. I think the one in the center. Oh no, I'm mistaken. I know I don't know which one is HIV and which one is SARS, but one of the two looks very familiar to most of you.
It's the one on the left is HIV.
I guess yes. So because of the spikes, I guess, and so all of these are images done with an electron microscope. Those are very expensive, and the problem there is also you cannot just take any sample because it's a very long procedure to dry it. And so for living cells, that's basically a no-go. And so, but still you want to study what's happening with these viruses, even though they are so small, because they are in the range of some hundreds nanometer. And so for what's important is to know, how can we build microscopes that can eventually resolve these particles. And usually you have optical tables full of parts, and this is just a random picture I took from Twitter. Twitter is the place for microscopists, it seems, where they just are proud to present their setups. So, and I'm in the field, let's say, for quite some time, and I have no clue what's happening there. So there are some laser going some curved lines and maybe causing some rainbows, I don't know. But it's a light sheet, it says, and so they but still it's a black box. And if you think about reproducibility in science, that's basically not happening. So how would I replicate that? And so we need tools first to understand it, and also then maybe to democratize it so that other people, not only here in this lab, maybe in other labs, maybe also aside from the US, can build it. And I think microscopes in general are a very nice tool to close the gap between the people who use it and also to build it. So I think I'm more of the tool builder, but I always appreciate if somebody is having a super cool finding. And so let's say our mission is to build fancy microscopes, to bridge the two gaps. And what are our tools? So we want to get rid of all the expensive parts. And so we have 3D printing, or let's say in general, like the maker space here. Let's say we have smartphones or electrical devices like a Raspberry Pi or some low-cost parts, and we have image processing. And together with these three ingredients, we can form very interesting assemblies. But first of all, some theory about optics, or like in the question, what is light? So I don't know who of you is familiar with like the physics of light, so that I can skip it or not. Nobody.
No, you should say a few words. Yeah.
Okay.
Yeah.
So who has seen this analogy that light is a wave or a particle? Okay. So I don't want to go too much into the wave equation stuff, but so in principle, light behaves, for me, in many cases, like a wave. So what I draw here is a point emitter. Think of an oscillator, which is just moving up and down, no matter what that means. And so what is happening there is the energy which is focused in this one point is just spreading in all directions. And if you plot that into the 2D plane here, that's basically the wave emitted by this point emitter in all directions. So if you were to draw a line from the center to the outside, it's basically a sinusoidal wave which is traveling in time. So that's, if you see one spot here on the wave front, so to say, that's basically the plane where every amplitude has the same, every point has the same amplitude, is spreading outside. So that means the energy is transmitted in this direction. And so the sinusoidal is nice because you can do all kinds of fancy mathematical things with it, and it's also lucky as a solution to the wave equation. So we don't need to derive anything. And you can also think about this in an analogy. If you throw stone into a pond of water, this is the same what happens there. So in many cases, waves light behave like waves in water, yes.
And just looking at that, you can think about what the speed of light should then be. What is propagating? How is information propagating, for example? What is that wavefront traveling at what speed?
Yeah, I hope that's obvious. But as I said, so these are, so if you were to represent the wavefront, as I said, points with the same amplitude value, you can see that along this x vector, the waveform behaves like a sinusoidal. So the mathematical form is plotted over there. So you have some terms which eventually shift the whole sinusoidal back and forth. So you have the zero, you have the maximum amplitude, you can have an offset. And the most important things are like the maxima, minima, and also then the direction where the light or the energy is traveling to. The lambda is basically 1 over frequency, which is basically the period of the waveform. And so the longer the wavelength means, like, you can translate into visible color to our eyes, the more red it becomes. The shorter, the more blue or violet it becomes. And so the lambda is basically the wavelength in optics. Well, not only optics, but electromagnetic waves in general. And so this is then giving us an idea for the visual spectrum. So we see everything roughly between 400 and 700 nanometer. So I think we can also see something a little bit below and a little bit above. But it's basically determined by the wavelength itself. So the wavelength is not the only factor which is important for us, but also the phase delay. So imagine you have a wave going through your pond. And now you have clear water, and then you have a gel-like structure. It's not like jello, but something in between. So that means the wave is traveling way slower. That means like the wavelength is going down. And that's the same with optics. So if you have different materials, so usually here we are surrounded by air, which is having a certain characteristics. It's called refractive index. And the wave just goes in all directions, basically unperturbed. But if you have now something like water or glass or all kinds of materials where the light could go through, the wave is basically retarded. So we are thinking about the air is unretarded and the rest is retarded. And so, for example, if you have in microscopy a sample, like for example your cells, the cell has a different refractive index as the water which is surrounded. And that means that this change in the refractive index causes deflection of the light, which can then be detected by the detector. So keep in mind, so the light has wavelengths, meaning color, but you can also measure the difference between an unperturbed and a perturbed wave. So that's important. Why? So if you were to measure gravitational waves, there is this instrument called an interferometer, which does exactly that. So this LIGO is an insanely large interferometer with an insanely precise laser. That means you compare a laser with a copy of itself. So that means you have this laser here, it's sending out light waves, and they travel to one mirror, and at the same time there's a beam splitter, meaning that the copy of itself is going there, and both of them are reunified here and going to the detector. So that means if you have a copy, it goes the same distance. So imagine the distance between here and here is the same on both ends. That means you compare two copies of itself without any difference. But imagine now, one of the mirrors here is shifted by a tiny little amount. If you have a perfect sensing mechanism, you could see even the tiniest motion of the mirror. And that's how they were able to detect gravitational waves, because this caused like a tiny shift in one of the axes, not only there but also at a different point on Earth, and so then they were able to correlate from noise. Because if I jump here, they may be even able to detect it there. I don't know.
Yeah.
But this is a very important principle for optics. If you understand this, then the rest is just
Question.
easy.
Is the beam splitter glass?
I have no clue how they implemented it.
Okay.
So I recently watched a YouTube video. So there's a podcast from one lady who built this thing. So if you're keen on getting more insights, so it's not just this year. So there's a whole bunch of optics involved. So, but it's really interesting. So
I think one comment that I can make, which we will talk about when we do the compliant mechanism session. The hardest part about this was how do you decouple it from all the vibrations on the planet to begin with. So although the optical components have to be ultra smooth and all that, on top of it, the massive engineering challenge was having these things be so precise and sitting even though there are other vibrations around.
Yeah.
So decoupling it without sending it to space, for example, which would not be viable.
Yeah.
And that took a long while And so if you watch the videos, you'll see this big mirrors, they're very heavy, you want big mass, but they are built around this massive machineries that are actively isolating it from any vibrations.
Plus, if you think about the refractive index, so air has, well, theoretically something around 1, so only vacuum has a refractive index of 1. But if you heat the air, then that means that the air is expanding, the refractive index is like varying. That means,
And you can picture that like if you have a fire, and if you have the fire, you see the waves, right? That's the refractive index.
exactly. And so that means, I don't know where this is exactly, but somewhere in the desert. So if it's heating up over a day, there will definitely be turbulences in this tunnel, which is 4 kilometers long. I think it's listed there, which is quite long for engineering. And you will see that. So I don't know who of you know, for example, these Canon zoom lenses that are used by these photographers from soccer games, the white ones, like they are like white beige. So the reason is, if you go to the desert and you take pictures and the optics heat up, that means there will be a change in the refractive index inside this lens, causing aberration. So they make it white, but it's not heating up as fast. So like this is one thing. Well, at least that's what they say. Maybe it's just a marketing gag. But it's interesting. Yeah. So there's a whole bunch of things in this device which is super amazing, and the data processing must also be very interesting. For sure.
I think interferometry is just in general a useful thing to know because the basic version is fairly straightforward to build, but it's just remarkably sensitive. And so when you're thinking about detection mechanisms and other places, it's a kind of an instrument that gives you a massive bang for the buck, because although the basic version is simple to make, the precision of this is just remarkable.
Yeah.
And I think I feel it's not exploited enough as it could either in the context of detection.
I mean, think of interference is happening everywhere. So it's just a question to measure it, to differentiate it from the noise. And the problem is also, one thing I haven't mentioned yet, so always the integral of the amplitude over time, which is basically then the intensity. So our eyes also only detect the intensity. That means the whole phase term, what I showed you here on the left-hand side, this is basically getting away. So what you detect is only the pure intensity. So it's basically the square of your amplitude. And if you square a complex number, the phase term unfortunately vanishes. So that means all approaches where you measure, so this can only be measured by decoupling it from the intensity term. So you have to have multiple measurements or an interferometer, which is a bit unfortunate. So I think you always have interference, no matter how, because you have always light sources from all different kinds. There's one here that's definitely interfering with that one here and also with that one here. But the problem in the end is the coherence. So how many different light waves come to one point, and how many, or what's the ability for you to differentiate it from where it came initially? So if you have a detector that can trace all the different directions and also the amplitude, then you could then everything stays coherent. But unfortunately, we don't have these detectors. Right. One more fun thing. So when they went to the moon, okay, so it should sound moon. They did a very fun experiment.
Is that a joke in German?
No, I think I was just tired.
That's something I thought.
No. So they brought a bunch of stuff. Besides a bunch of stuff, there was this little thing. Any clue what this is? Yeah.
Does it like refract light, like a mirror?
Did you say refract or reflect?
Reflect.
Reflect. Yes. So it's like a cat's eye reflector. So it's an array of different retroreflector, it's called. So meaning the beam that comes in is reflected with the exact same direction as it came in. So it's going out, it's curved basically. And so what's happening there is you can measure the distance from Earth to Moon by interferometry, because you just point two different. Well, basically you measure the phase difference between two different arms again, and then from the correlation you can determine the distance because you know the wavelength of your measurement device, and this relates to 1/meter, for example, and then you can measure that. And so there's a very interesting Wikipedia article which I read recently, and there's like, I think every state has their own challenge to be more precise, and it seems the moon is slowly drifting away. So so I think it's one of the measurements that lasts the longest. So I think like 70 years, no, 50 years, yeah. And different nations put up their mirrors, and it's a very interesting story behind it. Yeah.
So then there is a telescope that you can point to the moon, and you can find this mirror sitting there, right? So so every nation kind of does it, yeah. But it's super interesting. Yeah. No, I hope they knew the distance of the moon before they went and then put it, because there's a chicken and an egg. You can't go put the thing there.
Well,
so they must have other mechanisms.
Also finding that, I think it's
yes,
a
that's what
story.
I'm thinking about. Related to this is also a very famous. I think there's a talk by Feynman, but it was done by an artist, which is the world's largest painting, which was also just a series of mirrors put in the desert, tilted the right way to paint something, and it's said to be the world's largest painting. Oh, what's this happening?
That's a very
is it power?
No, it's but I think my computer is.
Okay.
I will come back.
Yeah. But you have charge there, right?
Yeah, it's
Okay.
charged. It's
Just plug in and plug it as a.
a bit overwhelmed. Well, so I think what I wanted to talk about now is basically light and matter interaction. Okay, my computer is a bit frozen. It will come back in a second.
Oh, there it is.
Is it?
You have to now
It's on its
mirror.
stand.
Yeah. You have to mirror displays. Oh, it's going to do it on its own.
It's the circle of death coming up right now. Well, yeah. So we don't always need to treat light as a wave. So luckily, we can also treat light as a ray. That means if we assume the light is not spreading in funny wave shapes, but all rays are parallel, we can also treat, as you may know that from physics school, that the light wave becomes a ray, and then we don't need to think about this whole thing about phase and stuff like that. It's just intensity along the direction. And then with this, for example, you can also do ray tracing. So if you, for example, in a computer game, there are these insanely fast ray tracers where you propagate light through a three-dimensional shape so that it becomes realistic. And also, if you want to, for example, calculate the lens design from your cell phone, this is all done with ray optics, because otherwise you could not be fast enough. This whole wave simulation is insanely complicated. Anyway, what's important though is how does the some things or some proof where this can be observed is a pinhole camera. I know who built it ever. It's super simple. Maybe that's the first task for Friday's hands-on session, where we just built a super simple pinhole camera. So you can build a camera with just a hole in a box. That means if you treat light as rays, every ray from an object has to go through this pinhole, and it basically just forms a copy of itself on a shield. That means you have the camera. So I think the camera obscura is the one you can look up. I think the oldest is somewhere from the medieval age. And so painters did like the paintings from landscapes, for example, in small boxes somewhere in a castle, and then super funny and old. Light matter interaction. So what is that? So light is traveling in space. We are in a space where, well, if I just look straight, the first thing which is hit by the light ray is the glass. So it partially reflects, partially it goes through. That means depending on the refractive index material, the waveform changes. And so depending on where, for example, something in space is located, you see that here on the right hand side, the light wave is bent, is eventually also absorbed in a very defined way. And I think the most simple to understand is maybe absorption. So what you see on the left hand side is basically what you did child, right? So like the rabbit thing, that's basically just blocking the light. So you just put something in the way, the light cannot go further, which means the light matter interaction means the light is interacting with my molecules, it's heating it up, and then since my hand is so thick, it cannot travel any further. The same mechanism is also used, for example, to detect colors. So the cell phone cameras are not smart enough to detect cameras, or like any camera cannot detect. Well, that's not true. There are some cameras that can do it, but most of them cannot. So the way you can detect colors only is by measuring it through a filter. So you have a red, green, blue, sometimes yellow filter that is laminated on your pixel. A pixel is basically just a sensor that detects how much light do I sense right now, converted into electrical charge or voltage. And then depending on what is the wavelength I would expect, you can then decompute your image. And usually this is the kind of spectrum. So over the wavelength, you have different paths through your filter. So you have a red, blue, and green band, and you have more green than blue and red because this is what our eye also doing. So we have more green pigments or like sensors in our eye. Because well, you can think about why that is. It's also a very funny reason.
So just on that, one thing to remember then is there's a consequence to it where color cameras will always have lower resolution because then you're taking, but if you had monochromatic, you could just get every one of those pixels. But here you've divided that up to call one true color into these 4 bins.
Mm-hmm.
And so when you buy cameras and you think about you're trying to detect something very sensitive, I think now the bare filters are bound. I'm trying to figure out. I think there are tricks of actually peeling it off. Right?
Oh yeah, that's.
So it's sort of a thread as you're thinking about. Oh, I buy something in one scenario, but I want to turn it to be much more sensitive for another function. And then of course there is this alignment between the pixel and that color sets many of the limits on the color cameras itself. It's quite fun to actually watch this.
Yeah.
So maybe when we do a session, I think if you take notes on, oh, I actually want to see a physical version of it, let's post that on Discord, and then all of us can scavenge around to say, hey, at least somebody brings a colored camera. Because one thing about the context of this course is what I was mentioning is the perspective of experience. You can read something, you can hear about it, but it's another thing when you discover the bare filter for yourself for the first time. And that's the real kind of that's when it integrates in your head in terms of, oh, I actually found this and it was true or not true.
Mm.
So I think keep that in mind for every much of the content that you will see through, that the Friday sessions would be about try to come up with the fastest, simplest way of proving the content that you heard about.
Yeah, and it's also then the next step maybe to follow up. So you have this image with red, blue, and green intensities, but how would you, for example, then visualize yellow? And so if you zoom in your JPEG image, there's definitely yellow, but it's not that obvious how you mix the 3 different colors to end up with a yellow pixel. So this whole processing, which is also done here on these beasts, that's a mathematical problem that's actually not so easy to solve. Also with like denoising, the fancy word is demosaicing and stuff like that. So it's very interesting to just look it up how that actually works. Right. So another thing which may become obvious is reflection. So if you have a plane surface that's having a high reflectivity, for example, like glass is an interesting material, but like a silver mirror, for example, where it comes in and the same angle it comes out. And I think in Chicago you may have seen the bean, it's chrome, also interesting to watch. And in London there used to be this building, I think now they at least did something to it so that this curved mirror surface is not becoming a parabolic mirror that's heating up cars anymore. So you can use that.
Oh, that's a molten car.
Yeah.
I just got it.
So
that's crazy.
Yeah. So you can imagine the curved mirror has a focal spot, and I don't know, it looks nice if you look it up. It's really like I don't know. It's a perfect parabolic mirror with a focal position exactly on the parking lot. It must be like, well.
That's hilarious.
Yeah.
Yeah, one comment I'll make about reflection versus refraction in the context of frugal optics. If you think about the original, most of the telescopes, and again, if you want to build a good telescope with the least number of parts, using reflection as a criteria, it's much easier because making one surface smooth is, from a manufacturing point of view, is easier than having two surfaces and having perfect materials. And this is a big challenge in telescopes. It can be done, but there are actually technically microscope lenses that also just use reflective surfaces. But it has not been exploited so much, and of course then the manufacturing ramped up. But when you see these very large telescopes, majority of them use the kinds of designs in which you're trying to optimize to have really good mirrors. But that's because making a very large lens is much harder than making a reflecting surface. And it's, again, in terms of thinking about sets of projects, if you can do something purely by reflection, try that first. But it's also not possible to do everything by reflection.
Yeah. And also these lenses are very expensive. But it uses, well, so for example, if you think about again how this piece is manufactured, so the lithography works at a very, very low wavelength. I think they are now somewhere in the range of 7 nanometers, maybe below. So this is called extra ultraviolet, I think, or extreme ultraviolet. And so there's basically no glass that is not absorbent at this wavelength. Also, the way they create this beam of 7 nanometers is insane. Having a drop of tin evaporating and then shooting that to a focus of the laser, and then eventually you have the excitation of this, whatever. It's a very long time didn't work, and then it's also wouldn't work because, so why do I tell that? So Zeiss is the optics manufacturer for this ASML company, and they basically developed all this imaging system which is purely based on mirrors. So if you ever look this up, it's insane how much
that was because they could not use the glass was absorbing too much.
Yes,
of that
yeah, so everything's done with mirrors, but the problem was they developed it before the source was even finalized. So they had a product without the source because the source was always burning away after some minutes. But it's, yeah, perfect use case for reflective optics. Refraction is also something where light is interacting with matter, but the way that, as I said, the speed of light is changed. So in vacuum, that's basically the fastest you could imagine, the speed of light. But as soon as the light is interacting with anything, it slows down. And that's also, I think, summarized in the Snell's law, it's called. And so here you have, let's say, we go from air into water, and think about this here as walking soldiers. I think that's also always the analogy, where they walk very fast in a plain field, but if this here is the beach and you have sand, they walk slower, but always all the same speed. So those here walking here still walk at the fast speed, and those entering here are slow. That means they have to match up all over the waveform in the way. And if you represent that again with the ray, you will end up with a bended ray of the surface. And why is that useful? So if you don't only have a straight surface but curved, you can focus a light beam, and that's what is done by lenses. And also again by fibers. So if you think about the image I showed you before, and the formula on the right hand side here, there's a point where you cannot solve it with the arc sign because it's not working anymore. And so that means the light ray is not refracted anymore, but it's totally internally refracted. That means there will be some sort of wave effect on the surface of the material. It's called evanescent fields, but most, like 100% in theory of the light is back reflected into the material. And you use that, for example, again, for transferring information through fibers. Yeah, this is totally reflection. Also used, for example, in most of the fingerprint readers. things back
One
in the
thing to
days.
remember is that's also a really fun Frugal component because many of those Christmas trees that some of you might have seen that light up, they have these types of fibers. And it's a very useful tool to bring light from one place to another, but for very cheap, because even a very simple polymer can do this, while you would need lots of complicated ways of getting light from one part to the other. And one thing Benet and I have been talking about for a while, it hasn't been done very well. Is it possible to print something like this on a surface just using a 3D printer? And suddenly then you have kinds of light guides on a given surface. So just because many optical components technically cannot be 3D printed, but fibers, for the other hand, can actually be printed. So it's this context of starting to really think about how much functionality can you add in the tools that you make with. And I think if you look at some of the resins very recently, there has been talks about printed plastic from some of the Formlab printers, for example, now. So they have some resins that are starting to come out where you could potentially just print your entire optical system. Which would be super exciting.
Yeah, that'd be cool.
We're just there, but I think in a couple of years, some of the resins will be at the point where they would have a decent quality. Because otherwise you have to mold them, and when you mold them, it's expensive from a prototyping point of view. Right now we use 3D printers just as printing your mechanical parts. But if it could print both mechanical and optics, that would be a huge bump. Yes?
By optics, do you mean like refracting and reflecting?
Both,
Or-
not reflecting, but refracting for sure.
Okay.
Yeah, I think they have one resin that they've been playing with for some time. It's not good enough to really do something serious, but on the other hand, the point is if you're starting to build certain sets of things where you need something but not have that much optical clarity, it might still be okay. But I just know that they have been working on that problem for a while. And again, I mean, I think because some of those techniques also have surface roughness that is low enough, and they have some post-processing that you can do as well.
Right. I think the biggest issue there is since it's a resin which is UV cured, you have to have an activator that's somewhere absorbed in an optical regime, let's say. Even though it's UV, you always see that if it's cured optically,
It's opaque.
that is opaque. So you always see this yellow
Thin.
yeah, so that's because it's absorbed somewhere. And the alternative could be, we can try something out maybe on Friday, like drawing your own fiber by just taking your hot glue gun and pulling it, and then maybe adding that on the top of your LED, and then using this as an evanescent field for your microscopy method. That's actually quite simple, and it's really impressive to see that.
Wow. Yeah. And I think just on that thread, one thing we'll do is let's remind ourselves, let's also bring some of the optically curable glue. That's the only one that I know that can still be cured and is clear enough, the Norland glues.
Yeah.
And a droplet, we have the very original full scope lens used to be, we built an entire kind of a system around using those glues as lenses itself. Because then surface tension gives you an atomically smooth surface, you don't have to polish at all, which is a huge challenge in lenses. So let's bring that.
Yeah.
So this way it will kind of, it's a sense of where does 3D printing and optics actually merge.
Can't you 3D print glass by just like heating the material and then
Yeah.
No, I think viscosity is an issue.
Yeah.
Okay.
Yeah, there are some art projects that do something like that, where they will heat very high temperatures, but then you get to the sense of, I mean, glass blowing, sort of, much of the physics of it starts to come into play, and this is the challenge of thinking about when you're trying to make these shapes, they're very particular shapes. And ironically, a project that we did a long time ago is we oscillated droplets of this liquid and flash freeze them, and then it turned out that mathematically those oscillations matched the optical surface you wanted. But that's a very rare, it was an accidental thing that we could achieve. But normally, and this is also where it's fun to think about in glass blowing as an art, I mean, we could spend some time on Friday actually making, currently it's not known how Leeuwenhoek made his first lenses, but there are two very specific techniques, so I could just show that. That might actually be, that's the closest to 3D printing glass for optics as it comes. But it is the origin point of microbiology and microscopy, because he made these ultra small lenses. So you could all try making some of these micro lenses, which is at the heart of full scope, for example. We don't end up using that technique because it's not repeatable. There are other ways to do it in a repeatable manner. But that would be what it comes closest in terms of 3D printing meets glass.
There actually was a demonstration from
Neri's lab.
No, there's a group, I think in Aachen, a German group that did a really compelling demonstration for glass.
Is it foreign optics or no?
That I don't know.
Yeah, that might be fun. Let's
Yeah,
pull
I'll
that
post
out
it on the
actually. It would be
Discord,
fun. Because I feel we are just on the cusp where, and when I talk about fluidics and hydrodynamics and microfluidics, we are also on the cusp that it is just feasible now to 3D print your microfluidics. And then suddenly if you can both 3D print your optics and microfluidics and mechanics, then the only remaining part is electronics, which doesn't have to be printed. It helps tremendously in the integration, the kinds of instruments that you can make.
So there are 3D printers for glasses, but they work the other way around. So if you have a block of glass, you shoot laser in there, and then either you vary the refractive index locally so that you add some porosity, or you remove parts inside the glass. So there are, I think maybe that's the company from out here. And other than that, you can mold your lenses with EMS and stuff like that. That's always an option for sure.
Which we can also do if
yeah.
people want. Actually, that would be a simple thing to do for optics.
Yeah.
Yeah.
And but just
We can try making our prescription glasses. See how much effort there is to replicate your prescription glasses. Because you could use your prescription glass as a mold, and that might be a fun project to think about.
Sure. So I don't have the slide here, but just to get a number, so the precision of these lenses from your microscope objective lens, for example, they are in the range of lambda over 20, for example, meaning somewhere in the range of 20 to 50 nanometers. So you have to have the surface roughness, or like following a perfect sphere, for example, which is as close as that. And the way it's done is by hand. So they have people who do that every day. So and there are just very few who do that. It's very interesting to see that, because the machines polishing the lenses are, I don't know, like 50 years old and so on. Because you have to have some certain randomness. It's completely done mechanically, which is not like CNC machines or so. It's all done manually. Really interesting. So I think I'm just skipping these things. What's interesting, going through some applications now, light guiding at home. I don't know whether you've seen this at all. So you can, there are certain different principles where you can get the sun into your house. There's a whole house in Switzerland using these light guides going through the whole house. So like they have pipes everywhere. They're filled with I think with water or some kind of oil that don't have bubbles, and then you can have total internal reflection in your house. Or in Africa, they use water bottles, so that they are like the interface between roof and your room.
And then just the origin story of that project, that actually originated from a guy in Philippines, again going back to frugal science. Even when it's daylight, most people's homes are dark. And the reason for that is they're made out of these tin shacks, but they are butted against each other, so it's not as if you actually have a window per se. The only thing that comes is from the door. And a person just playing around, and it turns out exactly the X-liter Coca-Cola bottle is the very particular one that they ended up using, because they tested many of those. It's just filled with water, and you can really just see it starts to glow like that. And then the project then scaled, and many people have actually been implementing these very directly, because it's a huge jump in terms of the amount of light there is, even in the day. Which is
water, just filled with
it's
water.
mostly filled with water, yeah. But it's very counterintuitive. Again, going back to context, sitting here we might say, oh, this makes no sense. If there is sun outside, why do you need light? Right? But on the other hand, if you're physically there, or you have a footprint there, and then you think about, no, it's actually the way the houses are constructed, even in daylight, there is no light. And I mean, again, this whole thing only works for daylight.
So splitting this up. So there's also an initiative to give people light at night. So you can recycle your old laptop battery, and then they make these battery-driven light sources, which is not from the people, but also very interesting.
Yeah.
A lens, as I said, is Snell's law, but think about every ray has its own. Well, think about the tangent here, there, meaning you have a Snell's law with a different incoming, outgoing beam, and that means that if you have the sum of all the beams, you can form a focus. I think the image is not quite right because the sphere is actually a very bad lens, but a lens can form an image on both sides. And if you have light that's coming from very far away, let's say from the sun, for example, it has light rays that are almost parallel hitting the Earth. It means the place where you form an image of the sun is its focal length. So that means the focal point is basically the point where you have the image from stuff that comes from infinity. The other way around, so if you have a point source, it's basically forming a parallel light beam that's coming out of the lens. That's actually very important. I think I'll come to that in a minute. Another thing which is frugal in coming to the lens part, so there are some people using parabolic mirror to heat up your lunch, but there's also some people using liquid lenses to burn stuff. So if you Google YouTube this thing, it's basically just a foil where people put in water and the what is called the force. Yeah, it's
The
forming,
gravity.
Yeah, the gravity forms a perfect aspheric lens. That means you have a focus spot with very high intensity because you focus the lens from like a meter in diameter, and it's getting very hot. And one other thing what we could try on the Friday session is building a liquid lens so that you have two membranes, you have water in there, a syringe, and then by adding the pressure, the surface is bending, and then with this you change the focal length of the lens, which is super frugal and I think fun to try.
And then the context, there is several projects on that space on tunable lenses with this liquid approach, both for doing eye testing. When you go to a doctor to get eye tests, they have a kit of these lenses. That's very hard for somebody to get their eye prescription. Now there are better ways of doing that electronically, but there was an intermediate time where this was a huge issue. And then the other part of that is also a manufacturing approach. There is a manufacturing approach for making optics for glasses, because glasses still appear. There is a significant portion of the world that does not have glasses. And that comes primarily also just, you need to change glasses as well. So the current programs are all donation programs, and you can see a huge issue around that because it's not, this is a distribution problem. Even if you have a donation program, you can't get people glasses. And there is a liquid lens based approach of making a curved surface and then use that as a mold. So you could make small scale manufacturing for glass prescription lenses.
Just thinking, time is moving very fast. So I'm just doing a quick dive. So just imagine, keep this in mind. A lens forms a point from stuff that is coming from far away and the other way around, meaning stuff you can propagate something to infinity.
You can think like magnifying glass, like focusing the sun to a spot, or magnifying glass, like letting you see the small thing.
Yeah, and so if you combine two of these magnifying glasses, you can form a telescope. First, stuff from infinity is focused, and then the second lens with smaller focal length is relaying this image, and then your eye is basically forming again an image on the retina from the infinity light. And a microscope is the same way, just switching lenses. So you have a small focal length lens, your objective, and something that's called tube lens, and the ratio of the two focal lengths gives you the magnification, and that's the whole story behind it. And I'm trying to think whether this makes sense. Maybe I just give a quick demo because I think Fourier is something that's very important in optics. So we talk about
And one of the things we'll be able to do is we can have some of this on the Friday
Yeah.
at the starting point itself, but maybe with more demos.
Yeah.
Because I think I'm thinking half of that Friday can be the start with demo of the materials.
Sure.
And yeah, so as you're thinking about content, we can shuffle as well.
Cool.
Yeah.
Good, so then I hope I'm not boring you too much. So interference. So wave 1 plus wave 2 gives the results, so the envelope kind of thing. And as I said, so there will be interference everywhere. And so what you see here is just interference over time. And so what does that mean? So if we have a spherical wave, so we can produce a spherical wave on the board here, but we can also just again think about it. We throw a stone in water with a barrier, then, well, if the wave is hitting the barrier only at this little slot here, the wave is going through. This forms a spherical wave, and this is just propagating. And it's propagating as long as it can if there is nothing in the way. And if you think about, okay, I let it propagate until infinity, that means these curves, at one point, they will just form a straight line again. So that means if you propagate something to infinity, it may become something called a Fourier transform. How is that? So I now don't have only one slot where light can go through, but many. This is then actually called a grating, so that you have on-off states where, again, the plane wave can go through. And that means now, think about, okay, we have one spherical wave here, we have one spherical wave there, and there. They all interfere. So you don't have only wave 1 plus wave 2, but you have wave 1, 2, 3, etc. And you basically form the integral of all the different waves. And what you can see there eventually, there is something formed here. So you have something like an order, which is going here, you have an order which goes here, and order that goes here. And why is that? It's basically the region where the light from all these different gaps in the barrier interfere constructively to form a discrete diffraction order. And this is basically done by a grating. So if you, for example, have a CD, you can nicely see that there's this rainbow effect, and that's basically the diffraction of the light that is reflected on the surface, or in this case, diffracted. And so, how can you calculate that? So usually you see you have this formula to map the different angles and colors to the wave. So what do we see here? So the zeroth order is basically the light that just goes straight through. That's the incoming light, and then you have the first diffraction order, and also you have the second diffraction order. And so I'm trying to make the bridge to the Fourier transform now. So the perfect superposition constructively from all the different contributions for migrating is only visible in infinity. So what means infinity? Could I just go infinity in this direction, eventually see this? So I think infinity is always the ratio between your wavelength and distance you measure. And since the wavelength of the light is always so small, it's already enough to go away a meter, or like maybe even just 10 centimeters to go to infinity. But what if you have small scales? Like, for example, you want to identify diffractive structures from a sample. Well, then you can visualize that using a lens, because what we know is the lens is also a Fourier transformer. So how do I do that? Okay. And the theory behind that, I'm coming in a second. So what we need to learn now is that the grating can have different structures. So depending on how far the different openings from our barrier are oriented, meaning the grating period, the more or less the structure is bending or diffracting the light. That means if you have a plane wave hitting our grating, if you have very small structures, the light is basically diffracted with a very large angle. So this is basically defined by this formula here. So that means smaller grating, larger diffraction angles. So, and doesn't make sense here now, I think no. So how can we use that? So if we now recall our knowledge from the lens produces an image from stuff that's coming from far away. We also know that if we have something in the focal plane of our lens, it again produces a plane wave. This is not only true for stuff like on axis, so if I have now here my scattering object, it's producing a plane wave, but also from a point that is a bit off axis. So now again, you can see the two different contributions, the blue and the red one, as individual waves. Wave 1 plus wave 2 gives our interference, but you can also think about the third contribution. So you have two off axis, one on axis. And if we now think about the lens as a Fourier transformer, which I'm just assuming now because that's the mathematical model of the lens, then in the focal length behind the lens, you have the Fourier transform of what's before the lens. And that's doing like something which is computationally very expensive in real time and basically at no cost. So a lens, as you know that, let it be your glasses or your cell phone lens, it's doing a Fourier transform since it's propagating stuff that's coming from infinity into the real space, basically this here. And so you have these discrete orders as you would see that with the grating. So why is that interesting? So in microscopy, as I said, there's this law which dictates you the resolution limit. So you cannot see anything below a certain structure. And so if we, okay, this is like graphically not very well done.
Yeah, and I think one thing that we'll do is we will redo some of the Fourier optics at the beginning with some demos.
Perfect.
Because I think when we do that on Friday, it would be valuable because then we can just sit one-on-one and do that as a demo.
Yeah, that's a good idea. I think we need some lenses to appreciate this. Otherwise it's very hard to understand.
Powerful. I think if you understand this concept, you really understand the most fundamental design principle of optics, because then optics goes away from being just geometrical objects to being mathematical objects.
Yeah.
And there's a very beautiful analogy in using Fourier optics as a way of thinking about getting stuff for free.
Yeah.
So it's very important even for Frugal. Lots of ray tracing and stuff that is conventionally used for designing. There's so many tricks that you can play with Fourier optics that, and I think we'll bring a few examples for that. Like we should do the Scotch tape cameras and so
that's a good idea.
So if you feel, I think this is a little bit fast in the end, we will redo some of this also for Friday, but with demos.
Yeah, that's a good idea. So I think what...
But you should still cover some of it.
Yeah, for sure. I will do that. So what is appreciable in the end is just this formula written in stone by Ernst Abbe. So it's surprisingly similar to the grating formula, where you have lambda over an angle, which is giving our resolution. The D in this case is the grating structure. That means it's limited by or it's linearly proportional to the wavelengths you have. So the lower the wavelengths, as I said, extreme ultraviolet, it's a very low wavelength. The lower or the smaller the structure you want to resolve can be. And
so D is the distance between two particles that are still resolvable.
Yeah.
And if they were smaller than D, you would not see them, no matter what you do, given a certain wavelength of light.
And resolvable, if people not saying object, it's basically like, can you distinguish between there being two particles versus one particle?
Exactly. So exactly. So I think in order to explain the whole theory, I would need some more time. Anyway, so there's something where you can see this formula in real life without any microscope or optics. So if you were to watch the stars at night, so what is your guess? So is there a difference in the size of the stars you can see at night? Some yes, some no. No. Why not?
Too far away?
So so I mean you could say, okay, maybe our
Exclude the planets. Yeah, this is for stars. Yeah.
Right. So if you think about this formula, like the distance you can see on a surface governed by the opening angle, so I should have told you about that, from our optical detection system, like our lens, it's determined by the way how much light can our eye capture. This is defined by our iris, which has a finite diameter. It's actually quite small. So that means we cannot resolve any better than the largest star, let's say. So that means every star has the same spot on the retina, so the same diameter, which is heavily aberrated. And it just appears that some stars may be larger because they are just brighter. So this formula from Abbe is basically visualized every night if you watch the stars. And that's also the same problem what microscopists are always facing, because you cannot go down to a certain limit. In light microscopy, that's, let's say, UV 400 nanometer divided by 2. That's roughly the dimensions we're talking about. Like 200 nanometers, you can differentiate a spot that's 200 nanometer eventually from something that's 300, but nothing below. So viruses, that's exactly at the edge, you cannot see. At least not differentiate whether it's a coronavirus or eventually an influenza virus, because they are roughly the same size. But you can. Yes?
What was alpha in the formula?
That's, yeah, so the alpha, I should have done the whole calculation based on this. So the alpha is basically the ability to collect light. So how much information can you collect? So that's the opening angle of your optical system. So in n times this sine of alpha is basically taking into account if you are, for example, in water, in air, so the immersion, let's say. So you can increase the opening angle by being in immersion media, for example, if you are in glass or something that